Okay, so in this video, we're going to talk about the ratio test, and the ratio test is one of the last ones we see for this topic. So the ratio test is you start with a series of terms an, and you take the limit of the next term an plus 1 divided by an between the absolute value bars. Okay, so you take the limit of the an plus 1 term divided by an. So pretend that we call that limit L. So if that limit is less than 1, the series is going to be absolutely convergent. We're going to prove that in a minute. If the limit is more than 1, then the series diverges. Sometimes we keep this here saying we leave this one in because infinity is more than 1, but technically if the limit is infinity, remember that we're here, it's an abusive language. Here, technically the limit does not exist. Right, so we shouldn't put in the same pile, so just write the limit, or the limit is more equal to infinity. There's a little bit of a boost in the language when we write equal to infinity, but we're not going to have any problems because if you understand it, if you interpret it that way, you're not going to have a problem. It's still more than 1. But mathematically, it's incorrect to say the limit is infinity. Anyway, so the limit is less than 1. It's absolutely convergent. And with the theorem we saw in the past video, we know now that if a series is absolutely convergent, then it is convergent as well, without the absolute value bars. So that's why this is a more general than it looks. Now, if the limit is 1, we have a third case, the test is inconclusive. Okay, so we'll talk about that also in the proof. So this ratio test has 3 parts, or 3 things outcomes. You take this limit up here, and you have 3 possible outcomes. You get the limit equal less than 1, more than 1, or if you have bad luck, you get exactly 1. In that case, it's inconclusive. Just, a little thing, this is never going to be negative, right? Because you're taking the limit of absolute values, so it's never going to be negative. Okay, so how do you prove this? So let's work this out. Let's see, the proof is has a great idea. I like this proof. It's one of those things in math that it's a very simple idea that you feel, well, of course. Okay, so let's say this. Let's assume that the limit when n goes to infinity of the next term divided by the an term is L and it's less than 1. Okay, so pretend it's somewhere right here. This is L, and the 1 is somewhere over here. So we have to be, it's a little bit here saying that the little thing we have to be careful is that, well, we can assume there's a number R, right, here. Let's pretend there's a number R, I'm going to call it right here. Okay, so L is not 1, but it's less than 1, so because it's less than 1, it's a very simple mathematical idea. Sorry, this looks like an L, like a 1. Okay, this is my L. If this is less than 1, there's a number R between L and 1, right? So this is a very simple mathematical thing. It's really a property of the real numbers. There is a number R between L and 1. So we write it R is between 1 and L. That's because I said this was exclusively less than, right? Not less than or equal, it cannot be 1. So it's a number between L and 1. Okay, now not only that, pick a number R, any number you want, but now for that number R that you have picked right there, okay, there should be a number N, I'm going to call it big N. This is the definition of being the limit, such that if n is bigger than that n, then let me not put the limit here. An plus 1 divided by an in absolute value is less than r. Why? Well, because the limit, let me put it, zoom in here. The limit is L, so eventually the numbers of these sequences are going to be here, 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 and eventually you have to get close to L. So eventually they're going to be less than R, correct? So just that's a very simple argument to say, so for n greater than n, this is going to be less than r, okay? So this means that really you break this up like the absolute value of an plus 1 divided by the absolute value of an is less than r, which is the same as saying, grab this guy and put it over here, right? Okay. So, oops, I didn't want to erase that. Okay, I just want to erase this guy. Okay, so having that, keep going. Do one more step. We can also have that the an plus 2 in absolute value is going to be less than r times the an plus 1, right? But the n plus 1 is less than r times an, so it's going to be r squared the an. Okay, so I'm just doing this. You can get this inequality by doing this, what I just said. You can grab that one in here. That divided by this would be less than r, so it's going to be less than that, right? This is for if n all under the umbrella, right, that n is bigger than that special one that we got, right? So keep going, and I really have that the an plus k is less than r to the power of k times the an, right? And now look at this. Look at this carefully. If I write the series, that I'm looking for of the absolute values of the ANs, like 2, I'm going to start from 1 to infinity, and I'll break it up between 1 and big N. Who is that N? This N, okay? Where it starts getting less than R, that difference code, that quotient, okay? So from N to 1 of these, and then start from, I'm going to here change the N, and put from K equals 1 to infinity of the a n plus k, okay? Now I have the sum of two series of positive terms, but this is not really a series. The first one, sorry, is not a series. This is just a sum of n terms. This is finite, right? I'm only adding n terms. And this one is convergent because this is right here. It's smaller than, this part is smaller than the geometric series with r to the k, so I can put I can write it like r to the k minus 1, and the an outside because it's a constant, and this is a geometric series with r less than 1. Right? Because that's the whole point. See, all this comes from this little simple idea that we had up here that, oops, my iPad got stuck, that the r is less than 1. And we have space between the L and the 1 to do this. Okay? So, there you go. I just proved that the series of absolute values is convergent because it's smaller than this term plus a geometric series that converges. Okay? So, the series an is absolutely convergent. And we're done. I'm not going to prove the part, so the ratio test has these 3 parts. I proved number 1, right? So I proved, let me change color here. I proved number 1. Number 2 is prove that if the L is more than 1, it diverges. But if you think about it, that's going to be straightforward from here, only that you would have the R on that side, right? And you have bigger than the metric series that converges. So, what we're going to show now is that why is it inconclusive at L equals 1? Well, because we have the example that we talked about in the last video. I don't know if it was a video or 2 videos ago. The example to show that it's inconclusive is talk about this one. You put n or n plus 1. This one is, if we know that this one, if you work it out, you can have limit when n goes to infinity of an plus 1 over an term with absolute values. You will get the limit when n goes to infinity of 1 over n plus 1 divided by 1 over n. I'm getting rid of the negatives because it's absolute value, so I don't care about that. So this becomes the limit when n goes to infinity. When you flip this guy, right, it's going to go in the top flipped. So it's 1 over n plus 1 times n over 1. So this is really just the limit when n goes to infinity of 1 over, sorry, if this is of n over n plus 1, and this one is 1, right? So this one, you get a 1, but the series converged, right? But if you do it with this one, you get a 1, and the series would diverge, right? Once you get the absolute values into this place, this looks the same, right? So if you get, if I use the ratio test on this series, I would get a 1. And if I do it on that series, I also get a 1. This one converges, that one does not. Okay, so it's not conclusive. Because we have an example for that. Okay, but let's see one that we do get a conclusion. So how do we use this? I just tell you an example. So let's write this down. For example, if I want to do it on this one, I can do the limit. So to do the ratio test, all I need is to find and use the ratio test. All I have to do is find the ratio of, the limit when n goes to infinity of the absolute value. I only have positive terms, so I'm not going to worry about the absolute value part, but I have to put it with the n plus 1 term over n plus 1, then divided by the n term. So I'm writing it right now, but in practice, of course, you can skip that part and you can exactly write the n plus 1 term as it is and the n term flipped, right? Okay, so this works nicely because if you think about this, the 2n plus 1 with the 2 to the n in the denominator really just becomes a 2 in the numerator. And remember that the n plus 1 factorial is really n plus 1 times n factorial. So in that case, this one cancels, everything in here cancels, and only an n plus 1 surrounds in the bottom. Correct. So that limit is 0. So the series that we started with is absolutely convergent, and hence it's convergent because the limit is less than 1. Okay. I may have time for one more before my video and time's up, and I can only post 15 minutes at a time. So let me just show you my next video. My next example. We're not going to finish this one. This one, if you do it carefully, it's a little bit interesting. 2n factorial on the top, n factorial square on the bottom. They're both fighting to go to infinity, which goes faster. A little bit careful to write down what happens on this one. So I think I'm going to leave it up there, and if you use the ratio test on this one, it's a little bit more interesting than the last one, but it's the same idea. Whenever we have factorials, we're going to use the ratio test because using the property that the n plus 1 factorial divided by n factorial cancels. Okay, look forward for our next video.